Okay.
So we start the afternoon session of today by talk of Professor Youjin Zhang, who is going to talk about Bihamiltonian integrable systems and their classification.
Thank you. So thank Anton and organizers to invite me to give the talk here. So my talk is on Bihamiltonian integral systems and their classifications. So, so let me first explain what the kind of Bihamiltonian integral system we are talking about. So the most typical example of this kind of integral system is the KdV equation, that which is the most well-known Victor-Solis equations, which is introduced by Keswick and Bryce about in 1895 to model this solitary waves, which was observed by John Scott Russell in the Union Canton near Edinburgh. So they write down these equations and give solutions which describe these solitary waves. So if we write this is a traveling wave solution, and this wave, if you draw this graph of this solution at t, for example, t equals to 0, it has a form of this form, and it's any time t, it keeps the form and traveling in the constant speed of 4k squared. So this is a very good example called solitary waves. And then actually in the paper of KdV, they also give the conoidal waves with periodic waves solution of this equation. But only after 70 years later, people find that apart from the solitary waves, they have so-called so-called multi-solitary equations, solutions of this equation. For example, if we take this tau as the determinant of this matrix, and then we obtain the so-called two-solitary solutions of the KdV equation. So if we write down, draw this picture of this solution, then at time t equals -5, we have these two solitary waves. And then these two solitary waves, the high one with high amplitude, it travels right-hand side, toward the right at a speed which is proportional to the amplitude. So it travels faster than the second one. So sometime later, for example, at t equals to -0.2, and these two solitary waves interact, and the taller one will catch up the smaller, shorter one. So then after sometimes it passes so at this time later, then we have this shape of the solution. And then at time t equals to 5, they separate again. So these are typical examples of the nonlinear interactions of we now call the solitary interactions. So this form, for example, if we take the speed of 4k1, the speed of the second solitary wave, at t tend to -infinity, we see this one traveling solitary wave solution. And then after t tend to +infinity, we see the same shape of the solitary waves, but with a shift of the phase. So this means after the interaction, the shape of the solitary waves are keep precisely the same shape, but only with the shift of the phase. So this is what Kruska and Zabutsky, they observed this very, very important nonlinear nonlinear phenomenon that possessed by the solid KdV equation. So this means that there are actually some integrability behind this solidity equation, so this KdV equation. So after this observation of Zabutsky and Kruska, they perform this numerical simulations on the initial value problem of the KdV equation. They find the kind of phenomenon. And then they realized that this KdV equation should possess some integrability. Then to show that this equation is integrable, this means that it possesses enough symmetry or should have many conservation laws or conserved quantities. So then people trying to find, apart from the conservation of the momentum and energy, they try to find some more conservation laws. Then Mueller, at that time, is postdoc of Kruskal. He trying to find as many as possible the conservation laws of the KdV equation. Then after some time, he find about 9 conservation laws of KdV equation. Then he stopped. He guessed that there should be more, but he want to continue. But then he realized that in the simulation of Kruskal and Sapolsky, there's another equation apart from the KdV equation. So in the KdV equation, we have 6u, ux, and then we have this equation. This equation also considered by Sapolsky and Kruskal, similar to the KdV equation. Then Mueller, also trying to find the conservation law of this equation. And he find, actually, there are also many conservation laws for this equation. In this equation we now call the modified KdV equation. And then he trying to find a modification of this equation again. He trying to not consider this v squared, but v for any power, v third power, fourth power. Then he find that there are no more any conservation laws apart from this you are now like energy and momentum conserved quantities. So this means that this KdV equation and this we can now call modified KdV equation are very special. And they show some kind of relation between these two equations. Then Mueller finds this relation, and now it's well known this Mueller transformation. If we write this u in terms of v in this way, then this KdV equation and this modified KdV equation are related by this equation. Then from this relation, if we modify this Mueller transformation by inserting some indeterminate epsilon, then from the conservation laws of this modified KdV equation, we are using conservation laws of the momentum. Then we can find infinitely many conservation laws of the KdV equation. We can solve this equation by in terms of u. We can represent W in terms of u in the series in terms of u, and each coefficient or powers of epsilon gives the conservation law of the KdV equation, because W is the conservation law for this, the density of conservation law for this modified KdV equation. So this is a very important step toward this discovery of the integrability of the KdV equation. Then using this Mueller transformation, we can write this, because this Mueller transformation is the equation of the Riccati equation. If we already know this u and want to solve this v, then we can transform this equation to a linear equation, second order linear equation. This is already well known. Then we introduce this transformation in terms of psi. Then this Riccati equation, Mueller transformation, can be write in terms of Schrödinger equation. So at this point, then Kruskal and his collaborators already know how to use this well-known scattering theory and inverse scattering theory, in which is already known in quantum theory, to consider the initial value problem of the KdV equation. So this is, I think, is the most important things that in the start of the theory of solitons. Then after this discovery of this inverse scattering method, then Lux realized that in order to relate this operator, we now call the Lux operator of the KdV equation, to it infinitely many conservation laws of KdV equation, we need to impose the evolution of the u, so that this operator L it also depends on time t, which is equivalent, unitary equivalent for all the t. So in this way, Lux, he realized that we can find some differential operators B, Bk for the KdV equation, we can write the KdV equation in terms of the commutator of this third order differential operator and this operator L. Then this gives us the evolution of the unknown function u. So, and then he finds that apart from the third order operator B1, we can also put some high order operators. So in this way, you will find actually not only the KdV equation, but also a hierarchy of evolutionary PDEs that can also be solved by using this inverse scattering method, precisely using the same scattering transform and inverse scattering transform. So this inverse scattering transform means that if we study the evolution of the, instead of studying the evolution of the function u, non-potential u, but we consider the evolution of the scattering data along the time, then this nonlinear problem converted to a linear problem for the scattering data, and then we use the inverse scattering to recover this potential u. Okay. So this formulation of the lux is very important step toward our more general understanding of this integrability of evolutionary PDEs. So after this, people find more and more solidity equations like KdV. So this is integrability that given by the Lux equations. And then another important aspect of integrability is what our title gives the Bihamiltonian structure. So this for KdV, now if we make a scaling to the KdV equation, we write this in this form. This we introduce this dispersion parameter epsilon. Then we can write this KdV equation in terms of Hamiltonian systems, infinite dimensional Hamiltonian systems. This means that the KdV equation can be represented as some Hamiltonian operator acting on the variational derivative of some Hamiltonians, log Hamiltonians. So this Hamiltonian operator P1 just equals dx, and P2 is the third order x derivatives. So this means that if we use these two Hamiltonian operators, we can define two Poisson brackets for the log functionals, and these Poisson brackets are bilinear and satisfies antisymmetric and satisfies the Jacobi identity. So these Hamiltonian structures, the first one is given by Faddeev, Zakharov, and Gardner in the 70s. And then the second one is given by Franco Magli also in the 70s and 70s. So what is the importance of this Bihamiltonian structure? So Bihamiltonian structure means that we have this such kind of equations relation we now call Bihamiltonian recursion relations. So if we are given two Hamiltonian operators P1 and P2, which means that they are compatible. So they form a Bihamiltonian structure. Then the first one in our case is this P1. So this P1, this Hamiltonian structure has a Casimir. So with the density of U, yeah. Then starting from the Casimir, we put into this Casimir h minus 1, k equals to minus 1, put here, we put k equals to 0. We have this right-hand side, we obtain the differential polynomial U. And then we solve this equation to obtain the H0. And then we put the H0 to the right-hand side, and then from the left-hand side, we obtain H1, and so on. So starting from the Bihamiltonian structure, and from the Casimir, the first Poisson of Hamiltonian bracket structure, we use this Bihamiltonian recursion relation to obtain an infinite many local function of HK. And this procedure can go through because we have this Bihamiltonian structure, means that the P1 and P2 are compatible. So if these two operators are not compatible, from the right-hand side, you cannot solve to obtain from the left-hand side, you cannot obtain HK from HK minus 1. Only we have this compatibility of these two Hamiltonian structures. Then we can solve this recursion procedure, recursion relations to obtain this H0, H1, and so on. And we obtain the hierarchy of KdV equations, high order KdV equations. So this Bihamiltonian structure is important. And so we obtain H0, H1, and so on. And then we have this KdV hierarchy. Okay. So then for this Bihamiltonian structure, we have we call it integrable. So in general, we don't know how to write down represent this Bihamiltonian integral hierarchy in terms of Lax operator, Lax equations. But anyway, from the Bihamiltonian structure, we already know that this hierarchy has each equation has infinitely many conservation laws. So we call them integrable. And then another aspect, very important aspect for us, is for the KdV hierarchy, is that it possesses tau function. So this means that this density of Hamiltonian HK, there is ambiguity. You can choose HK to put any total x derivative to this density of Hamiltonian, and the variation derivative is the same. So this ambiguity enables to choose this HK in a appropriate way, so that these Hamiltonians, the density of Hamiltonians, satisfy this we call tau symmetry conditions. So for the KdV hierarchy, we can find these density Hamiltonians so that this relation holds true. Then from this relation, we can find some function differential polynomials omega pq, so that this relation holds true. And this omega pq is symmetric with respect to the p and q. This is important. And using this relation, we can define the tau function in this way. So given any solution of the KdV hierarchy, and then we substitute this solution to this function omega, differential polynomial omega, we obtain the function of x, t0, and t1, and so on. And then we define this log tau function, so that this second order derivative of the log tau gives us this we call 2-point functions. Okay. So this we obtained the definition of tau function, and in particular, this unknown function of the KdV hierarchy U can be represented in terms of the second order x derivative of log tau. So this relation is already known quite earlier in the 70s. So people starting from Hirota, he trying to solve this KdV or other solid equations. He realized the form of the solid solutions of the non-solid equations, and finds that if we introduce some function like the tau for the KdV function, then this equation can be solved in a simple way. You can simply obtain this representation of the solid and multi-solid solutions. So he can transform this KdV hierarchy in terms of bilinear equations. So this is in the 70s. And later, Sato using these tau functions to relate the solid equation to the infinite dimensional Grassmannian manifolds. And then Jimbo, Miba, and Ueno, they introduced the notion tau functions for the monogeometry preserving deformation equations for some linear ODEs. And also they introduced tau function for some finite dimensional Hamiltonian systems. And this tau function also plays a very important role in our understanding of the relation of these solid equations with the representation theory of affine cosmological algebras. And so, and later, Dubrovin and I use this we call tau structures to study these infinite dimensional Hamiltonian structures, including these Bihamiltonian structures that we are talking about. So this importance of this tau function also plays very important in our study of the relation of the solid equations with matrix models with quantum field theory. For example, this KdV this KdV equation, very well-known theorem of Witten and Kontsevich says that this partition function of 2D topological gravity is just a particular tau function of the KdV hierarchy. So this is So this means the top function gives a bridge that establish a relation between integral system and the quantum field theory. So we have many, apart from the KdV hierarchy, we have also many Bihamiltonian integral systems that possess top functions. So for example, I thought starting from any n-twisted affine Quasimodo algebras, we can use the James-Sokolov reduction procedure to construct Bihamiltonian integral systems, which also possess top functions. Of course, for twisted affine Quasimodo algebras, we can also define some Hamiltonian integral system, but we do not have the second Hamiltonian structure. And also for some modification for some variant of the KdV hierarchy, we have this so-called Q-deformed nth KdV hierarchy, which is in certain sense a discrete version of the KdV, which is studied by Frankel and Stichin. And they are studies to focus on this the so-called Q-deformed W algebras. And also we have discrete integral system like well-known Toda lattice hierarchy and its generalization. All these are the well-known Bihamiltonian integral systems that possess top functions. And also there is a big class of Bihamiltonian integral systems of hydrodynamic type that arise in the study of two-dimensional topological field theory, and more generally related to Frobenius manifold as proposed by Dubrovin. So all these first three class of Bihamiltonian integral systems, they possess the so-called hydrodynamic limit. So for example, we have the KdV hierarchy, and we introduce this dispersion parameter. We can consider the so-called dispersionless limit, and we obtain a system hierarchies of hydrodynamic type of quasi-linear PDEs. They are still Bihamiltonian. They have the Bihamiltonian structure, and also they possess top functions. So in this case, we can write down very explicitly that these 2-point functions omega and represent in terms of tau, log tau. So this is the KdV hierarchy. Then what we are to study the problem is how to gives a good description of this class of Bihamiltonian integral systems which possess top functions and also which possess hydrodynamic limit. So what our approach is to study first the so-called class of flat exact Bihamiltonian structures of hydrodynamic type, and show for this class of Bihamiltonian structures, we can always associate to it an integral hierarchy of hydrodynamic type and which possess top functions. And then we consider its dispersion for deformations. And to study the classification of deformations of these Bihamiltonian integral hierarchies of hydrodynamic type. So, to study this Bihamiltonian structure, let me first give how to describe this Bihamiltonian structure for this infinite dimensional case. For the finite dimensional case, we are very familiar with. So let me first recall that we have a smooth manifold. We have a Poisson manifold. On the Poisson manifold, we have Poisson structure, means that on the space of smooth functions, we have the Poisson bracket, and which can be described by a so-called Poisson bivector. And so a bivector is a Poisson bivector, means that it's the shortened bracket, shortened knife bracket equal to 0. And this shortened bracket is I'll describe later. Then on a space of multivector fields, we can define complex using, if we're given a Hamiltonian structure, Poisson bivector field, and then we have a complex we denote by this D, this adjoint action, and we have this co-boundary, and then we can define these cohomology groups. And these cohomology groups can be used to describe the deformations of these Hamiltonian structures. Okay. So in the case that when the Poisson manifold is a symplectic manifold, then this cohomology, Poisson cohomology, is isomorphic to the dynamic cohomologies. But for general, we have this. Okay, so then if we have two Poisson bivector field, and we call them compatible, means that apart from this shortened bracket equal to 0, P1 and P2, then P1 and P2, they are compatible. Their shortened brackets also equal to 0. Then using this property, we can define a bicomplex by using this P1 and P2. We have two co-boundary operators. And we can define on the kernel of D1 the complex and define this cohomology groups of this complex. We call them the Bihamiltonian cohomology. Okay. So these Bihamiltonian cohomology can be used to describe these deformations of Bihamiltonian structures, and also to describe the Bihamiltonian vector fields. So this is a finite-dimensional case. Then for the finite-dimensional case, then we can also have a very convenient presentation for these Hamiltonian structures by using the supermanifold formulation. So we can consider this supermanifold of the original manifold M by reversing the parity with cotangent bundle Tm. We obtain this supermanifold. And then the multivector field of the original manifold M, can be described by the smooth function, spatial smooth function of the supermanifold. So this then gives a very convenient way to describe this shortened ninth bracket by using the canonical symplectic structure on this supermanifold. So this Poisson bracket, shortened bracket, can be written in this way. And here we use this theta and u as a local coordinates on the base manifold M, and theta 1 to theta n are the coordinates on the fiber. But then now they are order variables, not commutative. So we use this. And then we can use now for the infinite dimensional case, it's very convenient for us to adopt this super variable formulation for the Hamiltonian structures. For in this case, we still starting from a finite dimensional manifold M, and then we consider its infinite dimensional jet space, okay, as a projective limit of the case jet space or M hat. And on this M hat, we have this local coordinates u1 to un are the local coordinates of the base manifold, and theta are the coordinates on the fiber, the cotangent space. And then for the jet space, we have these local coordinates. You can view this u alpha p as a piece x derivative of u. You can view as a curve on passing through on the manifold M. And then we have this linear differential polynomials. Okay, we denote by a hat. And then we know that on this differential polynomials, we have two gradations, which is we are to use. One is the differential gradations, the powers of the orders of the differentiation. We have this one gradation, and also gradation for the super variables. The appearance, the times appearance of the super variables, we count as a super gradation, and we can define this homogeneous space of the two gradations. And then on this on jet space, we have global vector field dx. This is total x derivatives, and use this dx, we can define this quotient space. So then this is the space for local functionals that we are used to define the Poisson bracket or the Hamiltonian structures for the infinite dimensional case. And then so we did not assume this projection of a differential polynomial of the log functional differential polynomials a hat to this f by using this quotient space. Okay. then for the infinite J space on the space block functionals I've had, we also have this short Niles bracket. So here P and Q are log functionals of super degree P and super degree Q. And then this bracket is invariant and the change of coordinates. If this change of coordinates is induced by a change of coordinates given by certain, we call the Mueller type transformations. Okay. So then we can define what is a Poisson bivector field. So if a log functional of super degree 2 is commutative with itself using this shortened bracket, then we call this a Hamiltonian structure or Hamiltonian bivector field, Hamiltonian bivector field. So then using this super variable formulation, we can represent an evolutionary PDE. So we have this evolutionary PDE. For example, in the KdV case, we have this x alpha equals to u, ux plus u xxx, so the x derivative of u. So this x alpha corresponds to a log function of super degree 1. So it always can be represented as using this density as a differential polynomial of the infinite J space, which appear, this super variable appear once. So we have this super degree 1. So each evolutionary PDE can be represented with, by using local functional. And we say that this evolutionary PDE is a Hamiltonian system if there exists Poisson is a log functional super degree 2 P and the log functional super degree 0 H, such that the P is a Hamiltonian structure. This means that the P and the P is shortened bracket itself equal to 0, and this vector field X can be represented as a shortened bracket of H and P. So this Hamiltonian corresponding to this Hamiltonian vector field. So this is a Hamiltonian system. And then we have this, for example, for the K, then we also have a bihamiltonian structures. Yeah. So for the log function of super degree 2, we can always represent it in terms of, in the form this form. Is that this differential polynomial depends on 2 super variables each term. Then if we represent this in this form, so that this operator, this P, we can, from this P, we can obtain the differential operator P alpha beta. And we require this, that this differential operator is antisymmetric. Then this form is unique. Then we can obtain the Hamiltonian operator. So a Hamiltonian system means that as usual, we can represent the Hamiltonian system as the action of a Hamiltonian operator on the variational derivative of certain log functionals. So this is actually can be represented in the usual sense of what is Hamiltonian PDE. And then we say that this evolutionary PDE is bihamiltonian. So this means that we have 2 Hamiltonian structures, P1 and P2, so that X can be represented as the shortened bracket of P1 with one functional log functional H and P2 with another log functional G, and P1, P2 are compatible. They are Hamiltonian structures and they are compatible. So this is in the analog of the formulation of Hamiltonian structures of finite dimensional case. So then using this formulation, for example, for the KdV hierarchy, we can represent this the zeroth floor of the KdV, that this evolution coincides with the translation on spatial variable X. And this the KdV hierarchy, we can use this recursion operator to represent these densities of the Hamiltonians in this way, and then we obtain this log function of super degree 1. And then these Hamiltonian structures of KdV, we have 2 Hamiltonian structures. The first one is this P1, and the second one P2. Then we have this these P1, P2, these two log functionals corresponding to two Hamiltonian operators P1 and P2, and we have this Bihamiltonian recursion relations and so on. So this is a KDV Bihamiltonian structures. Then using this formalism, we can also define the Bihamiltonian homologies, cohomologies, and define the studied deformations of Bihamiltonian structures, like in the finite dimensional case. So then, so what I mentioned, that what we're considering is a class of so-called flat exact Bihamiltonian structures, hydrodynamic type. So we have a Bihamiltonian structure that is defined on, we look at the hydrodynamic type, means that they define on infinite dimensional just space with base manifold of dimension n, and we choose the log coordinates of the manifold m, v1 to vn. Then these Hamiltonian structures p1 and p2 can be represented by two Hamiltonian operators of this form. So this form of Hamiltonian structures is studied by Novikov and Dubrovin in the 80s of last century. They classify the kind of Hamiltonian structures and find that if this G is with respect to alpha beta is symmetric and non-degenerate, then this P is a Hamiltonian operator if and only if this G is a flat metric of this manifold M, and this gamma is given by the so-called contravariant component with Levi-Civita connection of this flat metric. So, so for this class of Hamiltonian structures, we are clear. So they always corresponding to a flat metric on the manifold. Okay. Then we require that the P1 and P2 form a Bihamiltonian structure. We need to impose some additional conditions apart from the flatness of G1 and G2. And so they form the so-called flat pencil matrix, which introduced by Dubrovin. And then we say that this Bihamiltonian structure hydrodynamic type is semisimple. This means that we consider this characteristic equation given by these two matrices G1 and G2, and we require that they have this n distinct roots U1 to UN are non-constant. Then it turns out that we can use this U1 and UN as the log coordinates of the manifold M. And then in these log coordinates, these two matrices, flat matrices, are diagonal. So we have this G1 and G2 represented by the n functions F1 and Fn. And then we can define what means the flat exact of these Bihamiltonian structures. So this flat exact means that apart from this Bihamiltonian structure, we require that there is another vector field on the manifold M, so that this vector field can be viewed as a local functional of superdegree 1, and then P1 and P2, this shortened bracket satisfies this relation. Okay, so also you can view it as the Lie derivative of this P1 along this C equals to 0, and the Lie derivative of P2 along C1, C equals to P1. So this we call the exactness of this Bihamiltonian structure. And then we say that this Hamiltonian structure, exact Hamiltonian structure is so-called flat, meaning that this vector field C is flat with respect to this flat matrix G1. So this is what we said, this class of so-called flat exact Bihamiltonian structures of hydrodynamic type. And then in the flat canonical coordinates, we call the U1 and U1, U2, and UN we call canonical coordinates. Then this we call the unit vector field Z can always be represented in this form. And then this flat exactness of this Bihamiltonian structures requires that the first flat metric is Yegorov, meaning that this coefficient satisfies the conditions. Okay. And then if we introduce this rotation coefficients of this first flat metric, we call gamma ij. This Egorov condition means that this gamma ij is symmetric. And this Bihamiltonian structure means that this gamma ij, this rotation coefficient, satisfies these equations. Okay. This is if and only if. Then, then in order to relate this kind of Bihamiltonian structure to some the so-called Frobenius manifold structures, we need to impose some additional condition called irreducibility, meaning that this matrix of the rotation coefficients cannot be put in a block form, block diagonal form, after a permutation of this index U1, E12, and N. So we impose this irreducibility of these Bihamiltonian structures. Then after this condition, then we will find that these Hamiltonian structures are always related to the so-called Frobenius manifold structure of Dubrovin. So this construction is actually standard, is given by Dubrovin's construction starting from any so-called kind of flat exact Bihamiltonian structure. So we can, given us this rotation coefficients gamma, we can consider this linear system, and this linear system have a through spatial dimension n. We can find the fundamental system solution psi1 to psi_n in a certain domain of the manifold M. Then we can define a symmetric non-degenerate matrix eta. This will serve as a flat metric of the Frobenius manifold structure. And we can also choose a local coordinates of this manifold M, we denote by V1 to Vn, by using these solutions, linear systems. And we'll find that this right-hand side gives a closed one form. So we can define this U1 to Un. And then these U1 to Un and using this flat coordinates, we define this flat metric of the Frobenius manifold structure. And on the Frobenius manifold, we have a multiplication on the tangent spaces. We define this multiplication using this by using this C alpha beta gamma, which is given by this psi, the solutions of linear systems. Okay. Then by using this construction, we can find a Frobenius manifold structure. We can define a potential. There exists a potential function f, so that this function satisfies the WDV equations. And then we have this unit vector field. So starting from any not semisimple but flat exact Bihamiltonian structure of hydrodynamic type, we can construct Frobenius manifold structures. But this construction depends on the choice of the solutions for linear system, psi1 to psi_n. You can choose other fundamental system solutions. Then you obtain different Frobenius manifold structures. But these manifold structures, Frobenius manifold structure, can be related by so-called Legendre transformations, which this because this WDV equation have some symmetries given by the Legendre transformations. And then this Frobenius manifold structure usually do not possess Euler vector field, do not have these quasi-homogeneity conditions. And then in order to construct an Euler vector field, we need to choose in a appropriate way these solutions of the linear system. If we take psi1, because this Euler vector field acts on the space of solutions of the linear system as a linear transformations, we can consider its eigenvalues and eigenfunctions, psi, eigenvectors. We can choose psi1 as eigenvectors of the Euler, of the action Euler vector field E. Okay. Then we choose psi1 to psi2 to psi_n as a matrix which corresponding to the Jordan number form of this matrix. Then we obtain this Frobenius manifold with quasi-homogeneous conditions. That means that it possesses Euler vector field. And we already know that starting from any Frobenius manifold, we also have two flat matrix, which form the flat tensor and gives a Bihamiltonian structure. One flat matrix is original flat matrix Frobenius manifold, and another one is given by the so-called intersecting form of the Frobenius manifold. Then these two flat matrices give us a Bihamiltonian structure, hydrodynamic type. But they usually do not coincide with original one that we start, because we're starting from a Bihamiltonian structure, hydrodynamic type. We construct the Frobenius manifold, and the Bihamiltonian structure that inherited from the original of this Frobenius manifold, usually they do not coincide. But if we choose some special, given a special choice of this psi solution to solution to linear system, choose this psi 1 using this these coefficients of the diagonal flat matrix, then we'll find that these two Bihamiltonian structures they coincide. Okay. Then starting from this flat exact Bihamiltonian structures, then we can construct an integral hierarchy we now call principal hierarchy. Okay. So we say that if we given Bihamiltonian structure hydrodynamic type, we are given a set of functions of different function of u, of a function on the manifold base manifold M, we call H alpha p. Then we say that this H alpha p forms a so-called calibration of this flat exact Bihamiltonian structures. If this H alpha p gives us densities of Hamiltonians, which we call Bihamiltonian conserved quantities, this means that if you use this H alpha p to form a Hamiltonian vector field with respect to the first Hamiltonian structure, then this Hamiltonian vector field is also a Hamiltonian vector field with respect to the second Hamiltonian structure. This means that these Hamiltonians give us bihamiltonian vector fields. Okay, and then these bihamiltonian vector fields have certain recursion relations given by this unit vector field C. And also there are some normalizations. Then the first H alpha minus 1 gives us given by the flat coordinates of this the first Hamiltonian structure, and this floor given by this I should write it the definition of floor given by the H alpha minus 1 these Hamiltonians. So by using this calibration, we can define a set of floors. We not call these quasi-linear PDEs the principal hierarchy. Then these floors are all commutative, and they have each floor has infinite many conservation laws. As this given by this H alpha p. Okay. So then a theorem of Dubrovin, Liu, and I say that given the calibration for the bihamiltonian structure for hydrodynamic type, then we have this principal hierarchy. Then this principal hierarchy possesses a tau function. These hierarchies are integrable. Integrable means that all these floors are commutative, and the density of Hamiltonians given by this calibration are symmetric because satisfy the tau symmetry conditions. And we can define 2-point functions, and using this omega, we can define tau functions of this principal hierarchy. And then we're using this omega alpha p, we can define a tau function. Okay, this omega alpha p we call a tau structure, means that this omega are related to the density of Hamiltonians, and they are symmetric, and also they are related to using this we can define the tau function of this integral hierarchy. And then we can define this given this constraint, given flat exact bihamiltonian structures, and we have this Frobenius manifold structure, and then we can construct this calibration. First, we can define set of function theta. theta alpha p using this recursion. Essentially, they are giving these constructions can be described by using this so-called deformed flat coordinates of the Frobenius manifold, of the deformed flat connection of the Frobenius manifold. So these functions we can construct these functions theta alpha p. Then using these functions we can define this density Hamiltonian H alpha using this formula. So we can actually given an algorithm to construct this calibration. Then using this calibration, we can define a top function for the principal hierarchy. Okay. Yeah. Then this theorem says that starting from any flat exact Bihamiltonian structure hydrodynamic type, and if we assume this semi-simplicity and also irreducibility, then we can give a calibration of this Bihamiltonian structure, and this Bihamiltonian structure gives us a Bihamiltonian integral hierarchy of hydrodynamic type, which possess top functions, and also actually they also possess Galilean symmetries and also Virasoro symmetry actually. So this is the class of Bihamiltonian integral hierarchy of hydrodynamic type, which possess top functions. Then what we are actually interested in is to consider their deformations. For example, we have this dispersion is KdV. Then we want to recover this KdV. So starting from any Bihamiltonian structure of hydrodynamic type, if we impose this semi-simplicity, we can classify their deformations. So it turns out that these deformations are parameterized by certain functions of single variables, we call C1 to Cn. They are called central invariants. And these central invariants, if they are uniquely determined as deformations, and if we also given a set of such kind of smooth functions, we can actually define deformations of this semi-simple Bihamiltonian structural hydrodynamic type. And then if we have a deformation, then we can also obtain the deformations of the associated integral hierarchy. We call it the principal hierarchy. So this deformation also always exists. Okay. So this means that we have actually too many a lot of integral hierarchies which possess Bihamiltonian structures. And if we impose more conditions, we impose the condition that this deformed integral hierarchy also possess top functions. Then we need to impose certain additional conditions. So if we impose conditions that our semi-simple Bihamiltonian structures of hydrodynamic type is exact, then you consider its deformations. These deformations are characterized by their central invariance, C1 to Cn, these functions or one functions. Then it turns out if you require that this deformed Bihamiltonian structure is still exact, then these central invariants should be constant. This means C1 to Cn. We cannot choose arbitrary central invariants. So for example, for the KdV case, we have this dispersion is KdV. Then we deform it, we obtain the KdV hierarchy. Then we can also deform the dispersion of KdV to obtain other Bihamiltonian integral hierarchy. The most well-known is so-called Kamas-Holm hierarchy, which is also describes shallow water waves. But in this case, we do not have top functions in our sense. Although this Kamas-Holm equation has similar properties of KdV hierarchy, but it do not belong to our class, which possesses top functions. So this theorem of Foucault and Lorenzoni says that in order to keep the top function property, we need to choose constant central invariance. And then if we choose the constant central invariance, then if we starting from a flat, exact, semisimple Hamiltonian structure, yeah, this theorem Foucault and Lorenzoni says that the exactness, if is related to this constants of the central invariance, but we are interested in the existing tau functions. Then it turns out that this constancy of the central invariance, even in C2, also guarantees that our deformation also possess tau functions. So this is the theorem that if we starting from a flat exact semisimple Bihamiltonian structure hydrodynamic type, and we have a calibration, and so we have a principal hierarchy. Then we can, if we choose this constant central invariance, then we also have a deformation of this Bihamiltonian structure, which still possess a flat exact structure. And also using this deformation of this Bihamiltonian structure, we can deform this calibration, we can deform these Hamiltonians to obtain the deformation of the principal hierarchy. So this is a theorem of a theorem that says that we giving any constant central invariance, we can obtain a deformation of the principal hierarchy associated to a flat exact semisimple Bihamiltonian structure. And their construction of this density Hamiltonian, we can construct this density Hamiltonian so that we can define the tau functions. Okay. So these tau functions can be defined using this formalism. So because this deformation of these Hamiltonians, we have some ambiguities. You do not know this choice of the representative of this density, the H alpha p. But anyway, you can pick any deformations of the Hamiltonians. Then we can choose this density of the Hamiltonians by using this unit vector field. We take this variational derivative of this original Hamiltonians with respect to this unit vector field. Then we obtain the densities, which is good for us to define these tau functions. So which satisfies these tau symmetry conditions. So this means that for us, we only up to now we only prove the existence of the deformations. So a question is how to give a constructive approach to find certain representative of the deformations of the flat exact semisimple Bihamiltonian structure hydrodynamic type with central constant central invariance, and to fix tau function, so that these deformations will give us candidates which will be used in our study of 2D topological field theory and all other theory study of glomulating invariance and other fields. So, for example, we can take, if we take this central invariance to be 1/24, then we can give a representative of the deformed Bihamiltonian integral hierarchy by using the algorithms given by Brown and I. We use this, we call the linearization of the Virasoro symmetries of this integral hierarchy to represent these Virasoro constraints in terms of loop equations. And from these solutions of loop equations, we can find certain quasi-Mueller transformations which transform this dispersionless hierarchy to the deformed, the full integral hierarchy. So in this way, we can give a constructive construction of this integral hierarchy. But if we choose this constant central invariant to be non-equal, for example, for the Drinfeld-Sokolov hierarchy, associated with non-simply laced affine Quasimodo algebras, for example, for B, C type, then we do not know how to construct this integral hierarchy. Okay, in our setting, means that we're starting from their dispersionless limit from the Bihamiltonian integrable hierarchy of hydrodynamic type and to construct this deformation. So this up to now we don't know, but we already know that for any choice of this central invariance, these Bihamiltonian integral hierarchies still possess Virasoro symmetries. Okay, but these Virasoro symmetries cannot be their action on the top function cannot be represented as the linear action of certain linear actions on the top function. They are more complicated. But only in this case of central invariance all equal to 1 over 24, the actions of the Virasoro symmetries are clear. So we can use this to construct this integral hierarchy. So I think my time is over. So thank you.
You can construct like a principal hierarchy, right?
Yes, we have this principal hierarchy.
So, for example, if you in type A,
yes.
Then you choose like 1 over 24, you construct an integral hierarchy.
Yes.
What's the relation between this hierarchy and the original
They're the same.
They're the same.
Yes.
Okay.
But if you starting from B and C type, you have this principal hierarchy. You construct this deformation using this algorithm or loop equation. You assume these central invariants are over 1 over 24. You obtain that topological deformations, not the general Sokolov hierarchy.
Okay.
They're different.
So you're expecting like a different one
yes.
in type B. Yes. Okay. Yeah. Okay. Thank you.
More questions? Thank you, speaker, again.
Welcome. Thank you.